Okay, so hi, I'm Henry. I just graduated and now I'm a corporate slave. But I used to be in CEVSOC with a couple of these guys, so I know these guys who are running it at the back. I see a couple of new faces that I've never seen before, but I assume you're like third years or something, taking steels for the first time. And yeah, we'll just kind of, oh sorry, there's another Play-Doh, I saw more people come. But this one's like the big W one. I'm gonna give everyone a Play-Doh, hopefully everyone has one. Yeah, nice one. This will help, actually I'll use this one for my explanation. This will help with understanding material properties and stuff a little bit about steels, right? Sorry? Oh yeah, sorry. Can you hear me better now? Yeah, okay. Basically, yeah, this will come a little later, but feel free to fidget with it basically for now. I just want to give you a little rundown of how this course works. So it's with Brian, right? I'm not sure if you guys have looked at the lecturer's name. Yeah, Brian Ui. I did it before with Hamid, who's a different lecturer, and so the course has changed a little bit now, but I can give you a decent idea of how it's run even with Brian, because last year he ran it, and a couple of my mates are doing it. The general course structures stay the same. So what tends to happen is you spend about half of the first week. Oh, hi Vina. Pranav. Hey, how's it going? Yeah, you spend half of the first week doing load combos, which I assume most of you guys, this is your first structural design course. So structural design courses, there's steels and concrete in term 2. They generally come up in third year, but I convinced a couple of people to take it in second year, concrete that is, just because I think it's, second year is filled with a lot of courses that are really abstract and doesn't really convince you that civil engineering is a fun degree. But trust me, these structural courses, once you do them, like steels, concrete, you really start to get into them, at least if you're me or whatever. But hopefully I can convince you today. So load combos. Basically, the point is, in Australia and in New Zealand, we use something called load combos, which we'll cover a little bit. And that's how do I say it in a non-over complicated way? It's just a way of exaggerating forces and stuff that you'll see in real life for worst case scenario kind of design, right? There's something we called strength design. So basically, how far can we push this building before it collapses? Essentially, that's what load combos are about. And load combos are not specific to steels, right? So you're gonna learn load combos, and you're gonna forget them, and then next term you'll do concrete, and you'll have to do them again, and then you just have to keep doing them again and again. If you keep deciding to do professional electives, which have structural professional electives and stuff. Anyway, this one's a good topic to really wrap your head around because it comes up again and again. And then the second half of the first week is tension, right? So we'll cover this a bit more, but I'll just run you through the different weeks first. So compression, flexural, which is another way of saying bending moment, basically. Bending moment design for steel. Shear design, so these words you might have remembered from earlier in your course, engineering mechanics and stuff like that, and solid mechanics. Connections, that's kind of a new term, but it's basically how two steel members are connected together or connected to the ground. That's kind of how you cover it. That's kind of what it's about. And beam columns is kind of the final topic, and this one's a really fucking hard topic basically. And it's generally what you would find in a final exam, because it's a combination of a lot of the previous topics. So the previous topics will show you kind of different parts of a design, different steps that you'll do to design a beam or a column. But then beam columns is fuck, we'll do everything, right? To design a part of the structure, a beam column interface, right? Today, I won't have time to cover everything because we've only got 2 hours and this is this whole course. So I'm going to try my best to run through tension, compression, and flexural in depth the most. The other guy who was supposed to be here, Shade, he was going to cover connections in a bit more depth, but I'll try to run you through his notes a little bit as well. But I didn't write them, so I'm not sure, I'm not as familiar with them, basically. And we'll talk about load combos a little bit. I'll try to gloss over it a little bit because you'll get a lot of time to understand them throughout the term. The more important things is to understand tension, compression, and flexural design. And basically, this is where the week 6 break is. In this course as well, you're going to be given like 3 assignments, basically, right? And these are like take-homes where you get given like a problem, and it's like unique to your ZID and stuff like that. And it's just going to take you a while to do, but it's basically you're getting paid marks for doing your homework, right? So it's actually pretty good. And yeah, like generally people do pretty well in the pre-exam stuff, which is the assignments. But once we get around to doing the final exam, Brian's final exam I heard was like decently easy, but I feel like it's going to make it a bit harder this year because final exams shouldn't be as easy as he made it last year. Anyway, does anyone have any questions right off the bat? Okay, if not, there's 2 bits of required reading for this course, like 2 kind of documents essentially. The first one's the Australian standards, right? So when you start reaching this part of your degree, actually no, I shouldn't say that. It's mainly just for the structural courses. We go off of the Australian standards, or sometimes the Australian New Zealand standards. AS New Zealand 1170. There's decimal points, right? So there's 0 and and then 0.1. This is basically everything to do with your loading. You won't really have to have a good look at these standards because they're just going to be really covered in depth in the lectures. Like everything you need to know that's relevant to the course will be in the lectures for this. But this is a part of like load combos and everything, right? This is where load combos come from. This is generic to all the materials. So even for concrete, you go back and you use these, right? The other one that's specific to steels is AS 4100, and this is the steel structures standards for Australia, and that's what the whole course is based on, right? So everything else basically in this course you can just find in this book. Yeah, that's required reading essentially. So time to quickly plug my YouTube channel. I have a YouTube channel called Sigma Lectures, and yeah, I'll show you the link for it in a second if you want to check it out, basically. But anyway, I have a video on here which is downloading the standards. Yeah, there's like concrete standards, but it's the exact same thing for downloading the steel standards. So that's how you access them. And you do it through like UNSW library website. The video covers it. Yeah. Here as well, I'll give you this link tree. There's like a link to this link tree. There's like notes for all the courses if you want them that are listed here. Not all of them, but yeah. What else? Oh, yeah. Okay. I didn't even include this one. This one's the first bit of required reading. As in, like, you don't need to just read the standards for fun, but like when you're doing your assignment, it helps to have the standards up because it has like every niche case on like how to do the assignment, and the assignment that you're given is generally kind of complicated because it's a take home, right? Yeah. The other bit of required reading is called One Steel Catalog. And these are basically steel products which are manufactured in Australia. And it's basically like, think of it like Legos, right? Legos come in like standard shapes and sizes. Steel products come in standard shapes and sizes. And they'll already have pre-baked a lot of calculations for you. Like, for example, the cross-sectional area, which we've called AG, like gross area, for a steel beam, for example, right? Something along those lines, right? These you can just access by going to Google and typing One Steel Catalog. And it's the top link here. 3rd edition steel, yeah, hot rolled steel products. And basically, let's go to, this is a universal beam. For example, it shows you on the top right what the product would look like. Has different sizes for the products. Like, this looks confusing right now because it's like, it's your first time seeing it, but it's fairly easy to follow. And it's gonna save you so much time because you're not gonna have to manually calculate every cross-sectional property. You just look at the catalog and you find the number and then you're set, right? It has a bunch of stuff on here, it's really easy. Yep. Question.
Like dimensional centroid and all
Yep. IX here. Yeah. So it shows you the numbers about the x-axis and the y-axis, which we'll cover a bit more in a bit. Elastic modulus, elastic section modulus, plastic section modulus, everything. Like everything you can think of which can be pre-baked. Yeah. Oh, my computer's lagging. Oh no, I hope it doesn't crash or some shit. Is my recording still working? Oh boy. What the fuck? It's kind of been... Oh. Okay, no, it works. It works. Let's go back to this. Oh man. Okay, give me a minute to fix... Oh no, jokes. This way. Okay. Come on, man. Okay. Okay, before we move on, does anyone else have any questions? That's just like the preface, you know. I've just gone over the preface so far. Yeah. Let's talk about structures. So essentially, there's a few different ways of thinking about structures. And in uni, we learn about pretty idealized systems. We learn about frame systems and truss systems, essentially, right? This goes all the way back to like 1300, essentially, right? So within a frame system, right, you can have 2D frames, you can have 3D frames. They're essentially the ones that are drawn kind of like this. You have pins, say like, well, you can have rigid supports if you want, but like you have rigid connections between the members generally. And actually the frames might look like this even, right? Yeah, these are all rigidly connected unless there's a circle there and there's a pin. Yeah, so it's things like that. That's like a frame, basically, right? And then within the frame, you'll have different elements, right? You'll have beams, you'll have slabs, you'll have columns, you'll have walls, right? But we probably won't talk about slabs or walls at all in this course. You'll talk about it a little bit, like slabs specifically in concrete, but we effectively just have to focus on the beams and columns. And so we're just thinking of those as like one-dimensional kind of members or elements, right? When you start thinking about slabs and walls, they're like two-dimensional, essentially, right? Okay, and next we have truss systems. So, you know, in real life, truss systems, they're not always perfect trusses, but in uni, we're going to consider them as perfect trusses. So, actually, does anyone want to give me like what makes a truss off the top of the head? Triangular shape, that's a good start. Pin joints, very good. Does everyone know what pin joints are? So like, for example, my elbow is a pinned joint. It can essentially rotate. So it's like connecting these two members and then it's free to rotate like that. That's pinned, essentially. So trusses have to be pinned. I've drawn them as circles here. They have to be pinned at every node, essentially, including, you know, the support. So you can't have rigid, you can't have like a rigid connection or whatever here for a truss. That doesn't work. And the idea is that trusses, like ideally, you want them to only take on axial tension and compression, right? So tension is when you pull something apart, right? Let me get this back. Split it out. Yep. So tension is like this, right? Compression is like squashing it together, essentially, right? So I'll whip out the Play-Doh again later, because when we factor in like material properties and stuff, how these two, like there's a lot of nuances basically to these seemingly simple kind of forces, essentially, right? So that's tension. And compression is going inwards, like that, right? Yep. So you'll find that in truss elements, essentially, right? Because of the way that, because of the way that the loads go onto the nodes, and then the nodes are pinned, essentially. Okay. Does anyone have any questions right now? With frame systems, I should have mentioned here, sorry. With beams, we find shear and moments. So if you recall back to 1300, right, you would have seen a lot of simply supported beams like this. And they might have like a distributed load or something on them. I've just drawn these lazily, but these are downwards arrows, right? So you have to draw the shear force diagram, you have to draw the bending moment diagram. That's going to come into play in this course because when we do like beam design and stuff, yeah, we're going to see like why shear and moments important, right? And then the other thing is for columns will take on compression and moments, but we don't really focus on columns as much in this course, more in concrete. So actually, yeah, we mainly focus on trusses and beams, I want to say, in this course. Yep. Does that kind of give you guys a good overview of what's going on? All right. Let me know if I'm going too slow. Yeah, I can speed up if you guys already know this, or if I'm going too fast or whatever. Yeah. So like Henry, shut the fuck up. Get on with it. All right. So this is new. This is called the capacity equation, right? So this is a generic expression, but the example I always like to give to explain the reasoning behind this is to do with tradies on a scaffolding system, right? Okay. So here's some tradies on a scaffold, right? And the idea is that on this equation, we compare external forces with the capacity of our structure. Our material and geometric properties contribute to this capacity, right? So capacity being like how much force can it take before it breaks or something, for example, right? So if we have 3 tradies, right, and say they weigh like 100 kilos each or something, quite heavy or something, and then, so yeah, there's 3 of them, there's one that weigh 100 kilos. If our structure, the scaffolding, can only support 300 kilograms, do you think that's going to be an issue? Yeah, no? Yeah?
Yeah.
Why is that?
The safety factors.
Perfect. So that's what this expression is about. It's about like introducing safety factors, basically. Because if we can exactly support 300 kilos and there's 300 kilos on it, well, you didn't design it properly. Because if this is considered a reasonable load on it, it's going to break, right? But that's why we have this star here, essentially. This star in this course will indicate that we've factored. It's called factoring. We've factored the external loads. That means we make them bigger than they actually are in reality. So instead of considering these tradies as being 100 kilos, we might consider them as like 120 kilos, for example, in our calculations. Say they just like ate a buffet like 5 days in a row or something, you know, like whatever. Worst case scenario kind of stuff. On the right-hand side, we have a similar type of idea. So this is called phi, like in Greek, it's the phi letter, but it's the capacity reduction factor. So we're reducing on this side. So we're basically pretending that the structure, instead of being able to take on 300 kilos of load, right? Let's say it can only take on like 250. We're just pretending it's a little weaker than it is. And this could be for all kinds of reasons. So if this is like scaffolding or something, it could be steel manufacturing error or something like that, right? Or it wasn't assembled properly, like one of the bolts wasn't put in properly or something, right? All kinds of reasons for why it might not be perfect. So we just bump it down a little bit for the capacity. Does that make sense, guys? Cool. So there's a bunch of notation you're going to see in this course. You get familiar with it. But yeah. R is like kind of a generic expression. You don't really see it too much in this course. But what I'm saying when I say R is it could mean all kinds of letters. It can mean NT, NC, M or V. Right, so, oh wait, sorry guys, this QR code, if I'm going too fast with my scrolling through the notes, if you scan this will bring you to a link tree. Yeah, and that link tree has all my notes, but if you click the top link on it, or one of the top links, it brings you to the Steele's notes, right, which is what I have up there. And this one's called Steele's Crash Course or something. So you can always just, yeah, you have a copy of the notes basically. Yeah, so anyway, there's a bunch of letters there for tension, compression, moment, shear, whatever. Yeah, I've explained that, okay. So in this course, generally you're going to find two types of questions, right? Oh, I should probably put this closer. Generally you're going to find two types of questions that are presented to you, right? The first one is the capacity equation satisfied, right? Which means, is the left-hand side of this, the external loads, less than the right-hand side, which is the material capacity, right? That's the first type of question. It's a simple yes/no question, and you just do, it's like a true/false kind of thing. And so in order to prove this, you kind of have to prove the left-hand side. So you do all your load factors, which I just ran over, and then you also do the right-hand side. And the right-hand side is a lot more complicated than it looks right here, because that's where all the steps come from. That's like the entirety of AS 4100, the steel standards. It's about telling you what RU is based on your, like the type of thing you're designing for. Like if you're designing for tension, if you're designing for compression, moments, whatever, right? That's the first type of question. So the second type, which is a little bit more nuanced, is about iterations, right? It's based on this loading which I'm giving you. How big does my section, right? When I say section, I'm talking about a cross section of a steel beam. How big does that section have to be in order to resist the loads? Like what's the smallest section I can get away with? And remember, the sections you can generally find on like one steel, right? Which is like the pre-baked products, right? So it's like, yeah, anyway. So it's like, which one can I select? That's the smallest. Because we want to not over-engineer it. If we just chuck the biggest section on there, you're going to waste a lot of money in real life, right? And that's against what the course wants you to achieve. So if you kind of pick the wrong one, in terms of you pick one that's like way too big, but it satisfies the equation, you might lose marks just because in reality it might waste money for like the company or whatever you're designing it for. But if it's too small, obviously it's unsafe, right? So that's arguably worse, right? So you want the sweet spot. Generally, you want it to be, I'd say like 20% bigger than whatever you calculate on the left-hand side. So what I mean by that is, say you have like, you get like 100 kilonewtons on the left, like your external loads. The right-hand side, with the factoring in mind, should be about 20% bigger, 10 to 20% bigger. That's what you're aiming for. If you go like 30, 40% bigger, you might not lose marks, but once you start going to like 50% bigger, yeah, that's a bit ridiculous, right? Anyway, so there's going to be formulas for something called initial sizing, right? You're going to try something and you're going to adjust it. Hopefully you guessed the right thing the first time around. There's a bunch of recommended numbers. So for example, for tension, it's 0.9 as like a guess for how much. It's hard to explain this. Like this number can change a bit depending on whether it's tension, compression, whatever. I've seen like 0.5, I've seen 0.2. These aren't in the standards. These are based on designer vibes, designer experience, feelings, because what's more important is what you get as the final output, Like this number is just kind of like generally if you run with this number, you'll get the right answer on your first iteration. Otherwise, you have to go higher or lower for your next iteration. Okay, like choosing a smaller, yeah, anyway. Any questions? Make sense? Cool. Yeah, okay, so one steel catalog isn't the end of the story, because like I said, the one steel catalog has like all your products on there, but a lot of the time, and especially in the assignments, you're gonna have to create a custom section, which means you have to do all the area calcs, like section calcs yourself, which requires a pretty good understanding of like solid mechanics, basically. It's kind of what solid mechanics is training you up for. So it's things like the second moment of area, elastic section modulus, plastic section modulus. If these words don't even like sound like words to you, then that's okay. Just we can go along, and you can always ask me questions even after the workshop, right? But yeah, so custom sections, harder. They take longer, and you're not really expected to do custom sections in your finals because it takes you long, unless you're me, because in my year. Anyway, sorry. It's fucking hard, isn't it? So, load combinations, right? These might look like this might not mean anything to you right now, but this is what is in AS 1170.1. I won't cover this too much because you're going to learn it as your first topic in your first week, and I think Brian will do a good job explaining it to you. But essentially, the thing you have to get familiar with is the fact that we start talking about loads a little bit differently now that we're doing steels and concrete and, you know, like real life design subjects, right? So G is known as your dead load, and Q is known as your live load, essentially. And you also see other ones. W is wind load. Things like this, right? More commonly just dead and live load. But the idea is that dead loads are things which aren't going to be moved for like 100 years, essentially. They're called permanent loads, essentially. And live loads are things which would move over the course of a day, a year, things like that. So the shorter term loading. And this is really important because especially for serviceability, which isn't really covered in this course, like how long something's been there makes a big difference on like the deflection of the structure and stuff like that. Like how much it's going to sag over time and things like that. Yeah. Yeah, so just an example, right? That column there, for example, acting on this floor, is that a dead or a live load, would you say? It's a dead load, right? So why is it a dead load, you reckon? Yeah, unless they renovate the building finally. But like, yeah. What about this whiteboard? Is this a dead or a live load? Sorry? Live, exactly, because I can just move it, right? Humans, live loads. These tables, they're movable, live loads. This desk, actually, okay, imagine this desk was like fucking like completely fixed to the ground and everything. That might be considered a dead load, right? Yeah, you get the idea, right? You start considering things as dead and live loads, and that's what you're gonna do in this course. Any questions? Yeah, just want to check. Okay. All right, so we need to start talking about material properties because so far basically, we've just been talking about left-hand side. So load combos and everything is just left-hand side of this equation. It usually doesn't take as long as the right-hand side, essentially. So all we've done is we've exaggerated our forces that are going to be applied to our building or whatever, right? Now we're going to be talking about the right-hand side. And the first step in understanding that is material strength, right? So specifically, here's what it looks like for steel. Yep. Oh, yep. Oh, yeah. Okay, so these are your exaggeration factors, essentially, for your loads. So there's a few different cases. 1.35 G means that you would, in the first loading case, is what this is called, you just consider the dead loads, right? So the things that are going to be there for 100 years, and then you add on 35% of it. That's worst case scenario number one. Worst case scenario number two is, okay, we'll consider the dead and live loads acting together now, right? That's having your dead loads again, exaggerating it by 20%. I'm getting that number from this, by the way. And then getting your live loads and exaggerating it by 50%. And the reason why you would consider, like, why this is higher is because live loads can vary more. For example, I think it was like Golden Gate Bridge or something. There was like a day where everyone was like celebrating its like 100 years, like Golden Gate Bridge or whatever, and they just all stood on the bridge, right? Fuck, you want the bridge to break or something? Like, what are you doing? But like, that's an example of why live loads are more volatile, and so this loading case is exaggerated a bit more than like the dead load only one, right? So you check the worst case scenario between the two of them, and what you do is you take the worst number, so the maximum between those, and I'd say just those, but there's other ones to consider. So between all of the ones you should consider, check the worst case scenario essentially. Make sense?
In the second one,
yeah.
is there a reason why you should
Of the dead loads?
Yeah.
Sorry.
Why can't you pick the 35%?
Oh, yeah, I see what you mean. Well, if you take 35%, essentially this one always becomes the worst case scenario. Do you know what I mean?
Oh,
Because it would always be this, and then, yeah. So it's kind of like I don't know how to explain it. It's like a combination of actions. So
because I feel like
Yeah.
in the first scenario, you constrain that dead load so at the worst situation.
Yep.
Second scenario, let's say people are.
Yep. People and dead loads. Yeah.
So why can't it be like dead load worst and also people?
I think it's to do with load durations, I want to say. So like, hard to like come up with something on the spot about this, but like,
Is that just the industry standard?
I think basically, I think they might have in like a very early version of the standards, and these standards are across like several different countries and everything. They might have just had one which was just consider. Actually, well, you always have to consider the dead loads, by the way.
Yeah.
In all of these, there's dead load essentially because the dead loads are always there. In another version, they might have just done that, and it would have underestimated kind of that worst case scenario. So they kept it as a dead and live combined action because they found in like the research and whatever that's just the most accurate number. I don't fully know how to answer that question because I don't know how they derive these, but yeah. Does anyone else have any questions? Okay. All right, so we'll move on to the right-hand side now. So that's capacity. The first step in understanding is material strength, and this is specifically for steel. So the good news about this course is you only have to think about one material, right? In the next course in concrete, you have to think about multiple because concrete is reinforced with steel as well. So the interaction of those materials is really kind of what does your head in. But here we just have steel, and steel's going back to, have you guys done material science 1101? That's 1101. Yeah, some of you have, I think. Yeah. Isn't it required now? I think maybe most of you guys have. Right? Oh, wait, but one of them. Oh, yeah, because there might be some fourth years here, right? Is that right? Okay. Yeah. Okay, so I'm just trying to adjust like how I explain this then. Essentially, material curves you might have seen a little bit of in solid mechanics, but they become pretty important as you go along in like structural courses essentially, right? This is a stress strain diagram, so stress on the y-axis, strain on the x-axis, and stress is essentially analogous to a force, right? And then strain is analogous to displacement, right? That's the very basics of it. So as you apply more force, you should think of it like in terms of the x-axis, right? So as you apply more displacement, right, there's this region that's linear at the start, and then it plateaus. So it's not taking on any more. It's not taking on any more force, essentially, right? And this is specifically for steel. So does anyone want to have a crack at why that happens? I like it. Okay, let me repeat that. So this first stage, steel behaves elastically, right? This is the elastic region. That means, so if I had an elastic band or something, and I'm stretching it, and then I let go, it's going to return to the exact same shape that I started with, hence the name, right? So that's elastic behavior. It's where there's no permanent deformation, essentially, right? Steel does that for a little bit, right? And then it plateaus. So why do you guys reckon it might plateau? What's happened in the steel?
Because it goes into the plastic region, and then
Yep.
When you stretch more and more of it, like it gets more plastic the more you go.
Yes, there's a word I'm looking for that in
Strain.
necking. Yeah, it's the result of it. But what's the steel doing? Yes, perfect. It's yielding. So that's the word we're using here. On the right. This is the yield strength of steel. So Play-Doh, why I have Play-Doh, is because it's basically a perfectly plastic material. This like deforms as soon as I put any like forces on it or whatever, and permanently, right? So this is essentially what steel does. As you apply more strain to it, it starts necking, like you said, but we call this yielding, right? So yeah, anyway, does that kind of make sense? But like, it's a little bit, Play-Doh might be like, sorry, Play-Doh might be like that kind of, I don't know. But like, here we consider it as like perfectly, like a plateau for a little while, right? Okay, the thing is, there's another region here, okay? This third region, what do you guys reckon happens here? Why does it do this? The steel.
Is it like parts of it start breaking and then it's completely all broken?
It's still part of the yielding process, actually. Keeps going up. So basically, it gets stronger. That's what we're saying. So this is a material. This is kind of material strength. So why does it get stronger after a little while? Sir? Yes, perfect. Oh wow. Okay, that was exactly what I'm looking for. So essentially, with metals, do you guys remember like chemistry and stuff? If you haven't done material science, you have like a metallic lattice, right? These little ions that are like connected to each other and stuff like that. Sea of electrons, all that crap, right? So the idea is that as you, let's just talk about tension. As you pull these apart, right, they're going to dislocate, right? But then the dislocations start impeding on the other dislocations. And so they're actually resisting its own like dislocating, if that makes sense. But then there's eventually a point where it just breaks. It doesn't want to take any more, essentially. But this is called work hardening. And it happens in like steel, aluminum, aluminium. Sorry, I don't know why I became American for a second. Okay, but yeah, does that kind of make sense? And so you reach this point called FU, pardon my French, and that's the ultimate tensile strength. You only really talk about this property for the tension part of the course. Yeah. Most of the design in the course is based on the yielding failure. Yeah. So we'll talk about that a bit more later. Okay. Okay, so next, steel grades. So steel grades are essentially to do with how strong they are in terms of like material strength, how expensive it is to produce, things like that, right? So there's a few grades you'll see in this course. 300 plus and grade 350 is what you'll see a lot in one steel and in like the tables and stuff. So if it says like, oh, we're designing a 300 plus steel section, whatever, it means that's what you should look at. So if the question gives you that, that's what you should be looking at in one steel. Like you go to the column which says 300 plus. It's kind of hard to explain. It's like going back to the Lego analogy for one steel, right? It's like, okay, the Legos are 300 plus, and then, you know, like the Lego off brands, there's like, yeah, that's like grade 350 or some shit. I don't know. Basically, they're slightly different, essentially. They have different properties. Make sense? Yeah. And then also there's a separate grading system for hollow sections. When I say hollow sections, we're talking about like kind of pipe shapes, right? So like hollow circular sections, hollow square sections, things like that, rectangular sections. Yeah, they have a different grading system. Yeah, you can look at this in more detail later. Okay, tension design. Sorry, we're finally here. This is the first week's topic that isn't load combinations, but I'll give you all that background because it helps for when I'm just talking about this stuff, essentially, right? So left-hand side, this is essentially truss design because you're not really going to find tension in non-truss structures so much, right? So just for the tension members and trusses. The left-hand side here is going to be external forces. So what generally happens is you're given a problem which, okay, either you're given just design for this much tensile strength, or you'll be given an actual truss. Like you'll be given a truss, so you have to use like all your truss methods, you know, like moment, method of sections, method of joints, solve it, and find whichever, one's like the worst case scenario for tension, and then design the tension member around that, like how big the steel section should be or whatever, right? Kind of makes sense? Yeah. Okay, but then the right-hand side is obviously where there's nuances. The capacity factor in this course is actually really easy. So if you've done concrete, capacity factor depends on so many things. It depends on like ductility of your reinforced concrete and like things like that. In steels, it's super easy. It's like 0.9 for almost everything except for connections and maybe shear. But 0.9, that's the number we reduce, like under-exaggerate our strength by. Make sense? Oh, capacity. Okay, so we have to check between two types of failure in this course, essentially, for tension. The first one is called yield failure, right? So if I have my trusty bit of Play-Doh again, right? This is yield failure, right? Where this yields so much to the point where the cross-section gets so weak it can't take the forces on anymore, right? Okay. That's the first type of failure. The second one's fast fracture. That's that. Do you see how fractured? Yeah. This is a brittle type of failure. Okay. And it's in the Play-Doh example just then. It's a don't pay too much attention about how fast I actually applied the forces, right? These forces are generally, yeah. So the difference in how which failure actually happens for steel is more to do with another property of fast fracture. Do you guys remember much from Maths 1101 if you did do it? Does anyone know what fast fracture is other than the example I just gave with this happening? Like what's something that might propagate that action? Like what's something that might cause that to happen, you reckon?
In steel, like specifically steel.
Yeah, or any material, but steel we're looking at, yeah. Sorry, say that again. Like short duration, high amount of loading or something. Yeah, that's essentially what I did here. That's true, but we're looking for a different thing based on the standards, actually. Let's just focus on. Do you say shear? Let's just focus on tension. So it says only tension being applied. What's something that might? Here's a hint. It's to do with something in the cross section. Something to do with the cross section. Okay. Basically, I'll give you the answer. That's yield failure. We kind of understand that theoretically, right? Let's go to fast fracture. If we have bolts running through our steel section, there's holes. Essentially, there's going to be holes in our section because we're going to need to use it to connect to another steel member. Why do you think the holes might cause fast fracture? Yes, pretty much. So it's kind of like to do with how. So these will be kind of like the new cross sections. Do you see how it's like? Do you see how it's like a bit smaller than our old cross section, right? The same amount of force has to go through less cross section, right? And also, it's partially to do with load. It's kind of like that. Yeah, like how the loads are distributed within the cross section, because like more loads will have to flow like that way, and like whatever. Do you know what I mean? Like, yeah. I think in Maths 1101, the very first experiment we do is like a tensile thing where there's like a crack in our Pyrex or whatever tensile specimen, and the idea is that it shows that cracks will propagate fast fracture, right? Yeah. Anyway, so these are essentially cracks, right? Like the holes will act as like cracks and reduce the area and everything like that, right? Okay, let's quickly have a look at the formulas which are involved essentially, right? So for yield failure, it's actually quite straightforward. It's do you guys remember the general like force equation? Oh, sorry, I should say stress equation. Like, what is stress? Very good. So stress is force over area, right? What if we wanted to rearrange that for force? That's essentially what this is. Let's do that. So the force that we're calculating, right, is going to be the product of your gross area. Gross area is area without holes, so it's the cross-sectional area, right? Multiplied by yield strength. So yield strength is the limit of the stress which our section can take, right? So that's why we have to do F instead of sigma for like the general stress expression, right? And we're looking at specifically this limit there. That's the yield strength. That's what we're going to be plugging in. That's fine. The harder one to kind of wrap your head around is going to be, is anyone still copying that down? The harder one to kind of wrap your head around is fast fracture, because it's to do with fracture paths. This is where it gets complicated, right? So imagine you have a section that looks like this, right? And you kind of have like this like grid-like pattern of bolts. There's multiple fracture paths. We call them failure modes. That can happen, right? So there's one where like the holes are not staggered, and then there's one where the holes are staggered. So which one do you guys reckon will be stronger? Kind of getting both answers. Number 2. Did I say weaker or stronger? So you reckon 2 stronger, but why do you reckon? There is more surface area. However, the holes remove surface area, right? That's true. So that's why we have to check, because it depends. It depends on how long the path is. Depends on how big the holes are. So it's a push and pull, right? And so we have to find the net area that's bigger, and the lower one, right? Like the weaker. Vina, are you okay? Does that make sense? Okay. All right. Yeah, the one that has like the less area will be the more critical one. That's what we had to design around, right? And then even between that, we have to consider both fast fracture failure and yield failure, and then like the lesser of the two will govern, right? The worst case scenario, the weakest one will be what causes it to fail. Does that kind of make sense, guys? This 0.85 is like a brittle reduction factor, because it's like a brittle type of failure. It just happens suddenly. Yeah. Sorry, yeah. Pretty much, yeah. Because otherwise, definitely just do both anyway. But I'm pretty sure fast fracture will only govern if, yeah, because we're going to be using FU. I love saying that. We're going to be using FU for this one, so it's going to be a higher strength. Do you know what I mean? So the only reason why it would ever fail before yield failure is if there's holes. Yeah, it makes sense. Because the holes will reduce. Yeah. That's why we have to check for everything, because everything's a push and pull. So sometimes you're going to be using a net area, but then you're going to be using the higher strength. But sometimes you're going to be using the gross area, but using the lower strength. Makes sense? So we check for everything.
So in that graph, yeah.
Yep, this one on the right.
Which progression would fail? Fast fraction.
So,
Go through the elastic and that flat base. Where would it fail exactly?
Oh yeah, so yeah, like on this slightly not drawn to scale graph.
That's for fast fraction.
Yes.
But it's going through all
the yield stuff.
Yeah.
Yeah. I see what you mean. I think the idea is like, basically once you get enough yield failure, it will just fracture as well. Like the fast fracture failure mode.
But what makes it fast fraction? If it's going through the yield, like normal, wouldn't that be like it's a yield failure?
Reaching the yield strength doesn't mean yield failure. Necessarily. Yeah. It's about yield failure kind of happens because it's like basically one mode of failure will show a bit of yielding, but the other one will happen so quickly and it'll be brittle that it's fast. Does that make sense? Like, yeah. So reaching this yielding point, there is a limit of how much of that is acceptable, because at a certain point the structure will just suddenly break as well. So one will give a bit more before breaking, and one will just break suddenly. But they're both considered failed in like the standards, right?
When you do that quite quickly,
Yeah.
it's that you're going through all of the stages, really.
I'll find a better explanation for you like in the break after. Yeah, but like yeah, because I can't think of it off the top of my head at the moment. This one. Do you guys want your break now? That's the end of tension. So we can go over like compression, flexure, maybe connections if we have time. Yeah.
Can you provide an example when N2 would be smaller than N1?
Oh, you're talking about AM? Yeah. You're talking about when A2 would be smaller?
Yeah.
I would say if the holes are quite big and the fracture path isn't very big, do you know what I mean? So like, this is a really exaggerated example, but do you see how the diagonalness doesn't offset the amount of holes? That, yeah.
Okay.
Yeah. Is that satisfactory, Lucky? Okay. All right. Yeah. Go have a stretch or grab some water or whatever. We'll be back in 5 or 10. Yep. I'll leave the QR code up so you can scan it.
So this is like week 1.
Yeah, that was week 1.
And then the next one is week 1. Still.
No. Tension's week 1.
Push-pull is week 2. So week 2.
Compression is week 2. Yeah. There's a lot more in compression design, basically.
So where are you really gonna cover week 1?
What?
Today.
Oh no, that's half of it.
Oh, okay.
Yeah.
Just sign in. Now we're just sign in.
Don't worry, we flagged
Yeah, that's what they always do.
Download, log in.
So all of this now using I'll show you my
Because this is the easiest topic.
I'll show you. Buckling. It's buckling. I like it.
Alright. For context, the stars is the difficulty of how I rated everything. So what we just covered is like 1 star difficulty, I would say. And then next week, as in like what we'll cover after the break, compression is 2 star difficulty. Flexure is one of the hardest topics. That's 3-star difficulty. And then shear is a little bit easier, and then connections is even a little bit easier, I would say. And then, yeah, beam columns is pretty hard, because beam columns is just everything, basically. Yeah. So, yeah. I think it was unlimited when I did it, but I don't know if it still will be. But there's like so much stuff you have to reference. There's like the standards. There's like one steel catalog. It's really hard to only bring one page. It'd basically be impossible.
For geotech, they gave us the standards.
Oh.
Yeah, like the standard booklet.
Really?
Yeah.
Oh crap!
Yeah.
Nice.
That was, they gave it to us like the start of the term.
Yeah.
And then they said, we're not
Yeah. Not bad then. But oh, I know what you mean. You're talking about the applied geotech notes. Yeah. Those are really good. But like, nah, this one I think you have to just print, like, you have to chop down a whole tree for your finals.
Crazy. Oh my God. I just haven't
All right, how are we feeling, guys? Do you want to get started again in 1 minute or so? 30 seconds. All right, we'll get started, yeah? Wait, did anyone go to the bathroom? Sir? Oh, Vina. Oh, maybe we'll wait for her. They're a work in progress. So, if you subscribe to my channel, if you subscribe to Sigma Lectures, I'll do weeklies. Yeah, and they'll be more in depth. I'm just running through the basics right now.
Are you taking one of the tubes?
No, I'm just doing it for fun. I'm graduated, but I don't know. I like teaching, so I'll just do it. Yeah.
Wait, are you gonna do them in person or recorded?
It'll be recorded. I'll just do it. Basically, I'll do it at my house, and then a couple of my friends will come over. But then I'll record that, so there'll be like a bit of like interaction in the video and whatever, like people asking questions. So it's a good check for me because like I don't know when I'm going too fast or not. So generally, like the questions is kind of like a good way to gauge that. All right, you guys ready? Let me just check this recording's still fucking working. Yeah, let's go. Lucky, pay attention. Yeah. Yeah. Oh. Sorry, I want to talk about one more thing. So this is still to do with tension design. KT, right? This is called the correction factor. And this is to do with, have you guys heard of eccentricities? Probably not. You talk about it a lot in geotech. Is anyone else doing geotech this time? Yeah. Okay, you'll hear about eccentricities a lot in the second half. Let me get up a good diagram. So basically, imagine you have a I-beam like this, right? And then we're doing tension, so it's being pulled apart. So where's the force going to be located? Like, where's the center of the force? In the middle, right? So this is essentially KT is equal to 1. There's no eccentricity. Got it? What about if we have something called an equal angle? So this is a steel product. It's called an equal angle, and there's unequal angles as well, right? So these are more like L-shaped. It's where the two bits coming off of it are unequal in length, essentially, right? But equal angles, yeah, that's just an example. Where is the force? Is it in the very middle in terms of D onto B onto? No, right? It'd probably be like, so that's B onto D onto. The force average or whatever might be there. Actually, no, that's probably wrong. It's probably somewhere on the actual steel member, right? So that offset is called an eccentricity. So eccentricity is just another way of saying an offset of the force. That is gonna change your correction factor. And so there's a bunch of rules to do with it on the lecture slides, right? Yeah, you can have a good read of that, but it's just to do with whether the force is applied in the middle or not, essentially, for tension, right? And the correction factor is only in fast fracture. I can't tell you why. Yeah. Oh, so if you think of a truss member, right, and in like 1300 and stuff, we just think of it like a straight line. So we just think of it like a one-dimensional object, right? And so the tension's just running right through the middle, right? But since steels, we start thinking of things in 3 dimensions. Essentially, you think of the tension like more of a stress rather than a force. So it's kind of like a bunch of little arrows, right? Just pretend that's an I-beam. I know that's something else. Do you know what I mean? So it's like a bunch of mini arrows everywhere that's pulling it. And so the average of that is where the force is going to be located, right? Yeah. Okay, you guys ready to move on to buckling? So the next 2 topics, which by the way, let me just give you guys an idea of how big these topics are. Compression takes 2 weeks, 2 and 3. Flexure takes 2 weeks, 4 and 5. Buckling is to do with both. And so buckling covers like half the course, essentially, right? This is like one of the most important concepts to keep in mind, essentially, right? So, this isn't going to be the best example. Does anyone have like a ruler or something I can use? A ruler. Okay, pretend there's a ruler. Pretend there's a ruler, right? If I squish down on it, right, that's compression, right? That might be like compression loads acting on a column, for example. Is it going to perfectly squish up, essentially, based on this shape? What's going to happen to it? Is there going to be any like eccentricities? Right? Yeah? So why is that? So our column is going to buckle. So buckling is where it goes off its center as you squish down on it, right? That's the general concept. Okay? And what happens is if we have a shorter column, for example, like this, yeah? If I do push down on it, it does stay in the same like line of action, I guess you can call it, right? So buckling is a function of how long your member is. So the skinnier it is, so how long, kind of like divided by how wide it is, essentially, right? So this is like slender. This slender column might be classified as this. A stubby column is classified as something which the length to width ratio is like smaller, basically. And so slender columns are really susceptible to buckling. Okay, that's the general idea. And buckling happens for not only compression, but flexure as well. We'll cover that a bit more, but let's just focus on compression. So compression being me just squishing down on that like, as if it's an axial force. Right? Yeah. There's going to be a bunch of stuff, which, yeah, so that's essentially buckling, what it looks like. Okay, the thing is there's different types of buckling. So a couple of you guys, I know, have done concrete, and no, concrete doesn't really focus on buckling. Okay, never mind. Basically, there's two types of buckling. There's local, or sometimes called section buckling, and there's global, sometimes called member buckling, sometimes called Euler buckling. And do you see these diagrams? Like, pay attention to them. What do you think, like, why do you think they're different? Like,
is the global one like over the whole beam? Like
yes.
the whole section, and then
Perfect.
And then the local one is just like in that example, it's only applied.
In the cross section, within the cross section, right? So there's a different axis we're looking at, right? So in concrete, right? So say you have a concrete column. Pretend that's a concrete column. Generally, they're shapes like this, you know, rectangles and things like that. They're not really susceptible to local buckling. You only really consider the Euler buckling or the global buckling, right, along its whole length. But for steel, because steel members are generally pretty thin, they're pretty slender, like the one you can see there. What happens is they can sometimes buckle within the section. I should probably tell you guys what parts of the section are called and like how they're classified, because I forgot to mention that. So we have this and this. These are called flanges. And this is called the web. Okay? That's just terminology. So it's actually based on the width, right? So like when I say width, I'm talking about this dimension, yeah? So flanges have a higher width, like it's the one that's wider, and webs are the ones which are thinner, and generally like more of the depth, right? That's just terminology. So do you guys reckon that flanges or webs are more susceptible to buckling in general?
Web.
You sure? Say they're the same thickness. Say they're the same thickness. Like why do you say that? Like yeah, just I want to see your thought
Wait,
process.
like in terms of what's the loading case?
So compression. It's just similar to what we saw before, but it's being pushed in together. So it's all like stresses are being applied like little arrows throughout the entire thing, right?
Like along the y-axis or the x-axis?
Axially. So like that.
Oh, okay.
Oh, I see what you were trying to say.
Yeah.
That's you're kind of thinking about flexure. So that's to do with bending. Right now we're just thinking about axial compression. Yeah. Okay. Okay, do you think webs or flanges are more susceptible to buckling?
Would they be the
Local.
same, like,
If they're the same thickness.
wouldn't they be susceptible to the same amount?
There's certain areas which aren't as susceptible in this section that you can see to buckling, to local buckling. Farhan?
And on the second one, or measure the I-axis.
Not really. Okay, I'll just yeah.
Are there like certain regions where it's more susceptible?
Yeah.
So like at the end of the fund.
Yeah. So why?
It's because it's not like supported
Yeah,
by
exactly. Yeah, that's right. So here, where there is like an interface between a web and a flange, we consider it can't buckle, right? The further away you get from that point, the more susceptible it is to buckling. Does that make sense? And for the web, sometimes the middle of the web can buckle. That's possible, but it's supported from both edges, so it has like that rigidity on both sides. But most likely, it's from the tip of like the webs is where buckling happens. Make sense? That's kind of the logic you want to follow. Does anyone have any questions to do with that? That was to do with section buckling, right? Like the individual elements within the cross section. But yeah, anyway. So what I said before was buckling is a function of your length divided by your width or whatever, but that's actually slightly incorrect. It's actually to do with effective length over radius of gyration. Radius of gyration is that random ass like section property which you don't even think about and you don't know what it's used for. Here's what it's used for. It's used for the slenderness ratio, right? It's the square root of your moment of inertia divided by area, essentially. Okay. And effective length, we'll talk about effective length later. I see people copying this down, so I'll give you a few more seconds.
Radius of gyration, is it just like, it's like, because it's from the centroid.
Yep.
And then, well, what does it mean by like radius of gyration? Like, does it mean like the distance of which it's actually the maximum and then
Shit. How do I explain this? I've never found a good way to explain radius of gyration other than just like looking at the formula for long enough. But like, say you have an I-beam, and then pretend it's like a literal radius.
yeah.
The idea is, sorry?
And then we'll stay confined within that circle, right?
Not really confined. It's more like kind of. So do you know how I said before? Slenderness is to do with the length to like width ratio. That radius of gyration is kind of like a standardized width, but for your section. Does that make sense? So you kind of, it's kind of bad to say, but you can. It's not very accurate to say, but you can pretend like we're treating that I-beam or I-column as kind of a circle cross-section, and then we consider the buckling based on that slenderness. Does that make sense? Yeah. It only kind of makes sense to me as well, so yeah. But you'll find R in one steel, right? You'll find the radius of gyration on one steel. Yeah. Unless you have a custom section, which most likely is what you have to do for your Flexural assignment. Yeah, it's AIDS. Okay. The last thing I want to mention is that buckling is an elastic mode of failure. So in terms of your material curve, you actually never really cross into the plastic region for it to fail. Because it's doing this, but none of the material has actually permanently deformed. So if I unload it, it'll unload. It'll return to its original elastic shape. Make sense?
So buckling is only in the elastic.
Buckling can cause a plastic failure later on, but it will weaken your member significantly. Yeah. But buckling effects only really kick in when you have a slender member. So if you have a stubby member, you essentially don't have to consider the effects of buckling. So like this thing again, right?
Yeah.
Yeah, but slender members, their material strength, like what we calculated in like tension, for example, but the compression version, the material strength gets significantly weakened by buckling effects. Yeah, make sense? Oops. Yeah, last thing is I'll quickly talk about form factor. So form factor is essentially what I was talking about with, do you remember the section thing we were talking about? The parts which will locally buckle and the parts which won't. So essentially we're going to consider it in terms of effective area. Effective area is your blue area there, the bits which won't buckle, locally buckle, right? And then the red is the ineffective area, so the bits which will buckle locally. So I'll give you just a quick pop quiz. If our members were thicker, are they more or less susceptible to buckling? Like the flange and the web, if they're a bit thicker? Yeah, exactly. So you're kind of considering this like length to thickness ratio, but for every individual element on your section as well. Make sense?
Yeah.
Okay. And then member failure. So global failure, basically. So that's the one where it bends like that, right? The thing is, to calculate this, you have to calculate the section first. So you always do the section failure first. What do you call it? The compressive section capacity first before you do the global one, because it's dependent, right? The formula is dependent. And so the end goal is to find this thing called the compression member slenderness reduction factor. And here's where you just go down a rabbit hole of folders within folders, so to speak, of formulas to follow. So you got this one from the previous step, which is the capacity. And in order to find alpha C, you have to find alpha B, and you have to find gamma N. And gamma N has two other components, which I forgot to copy over, but you'll see them. So it's kind of like a rabbit hole. You're just trying to find little bits and bobs, and then when you have these two bits, you can get this one too, essentially. It will be in the workshop questions, it'll be in the exam, it'll be in your assignment, yeah.
Because you said it takes a lot to
Oh, yeah, sorry, I should also mention, this one, KF takes the longest to find for a custom section. But that's only if it's a custom section. So if it's on one steel, it gives you KF. It'll tell you KF is 1, which means that none of the individual elements will buckle. Or if it's less than 1, it'll tell you the KF that you need to plug in. So it's really easy. It's just when you have a custom section, you need to like fine tune it or whatever. It takes ages, basically. And there's a bunch of rules for it and stuff and everything. So basically to find, so we're looking for a bunch of things, right? We're looking for number 1, alpha B, and number 2, gamma N, right? And so alpha B is not bad. It's from a table. And essentially, most of the time you're going to be dealing with hot rolled UB and UC sections. UB stands for universal beam, which is just another way of saying I-beam, I-shaped beam. And UC is a universal column, which is which is like a I-shaped column, basically, right? Hot rolled is anything you can find on one steel. Everything on one steel is considered hot rolled, and that's just like the way it's manufactured, essentially. Make sense? Yeah. If KF is less than 1, so if parts of it are ineffective, right? Like say that's ineffective, that's ineffective, that's ineffective. You just follow a different table, but it's based on classification, essentially. Okay, gamma N, modified member slenderness, is going to depend on 2 sub-factors. Sorry, I forgot to write them above. The first one's effective length, okay? So we're gonna talk about that. And then the second one is radius of gyration. Okay, so here's where we're getting into that buckling theory. So, okay, basically, effective length is the length multiplied by some kind of factor, right? So LE is K times L. So say your compressive member, let's say column, it has a certain length, right? Like that. So the things which this factor depend on, actually, do you guys want to guess? What does this K factor depend on? What do you think changes the effective length, aka how much something would buckle?
Like in terms of strain.
Sorry, don't think about material properties right now. Think of
The balls.
sorry? We're not really thinking about the cross section. We're talking about the entire length of the member at the moment and how much of it we'll consider in our length. So that's effective length, essentially.
Where it's connected to other numbers?
Kind of. So you're on the right track.
How it's
Yep. So spit out some words regarding.
Like one of them is like free. It's like these
Yeah. So it's about the fixity of the connections and about the supports. Yeah, to like the ground and things like that. Exactly right. There's one more factor to consider. Think of trusses. Maybe not trusses. Think of a frame like this, okay? And think of it taking on like lateral loading, say from a wind or something like that, right? What's gonna happen to this frame by itself? Sway, that's the word I'm looking for. That's called a sway frame. What happens if we do this?
It's going to be stable.
Yeah, against like wind and lateral loads, right? That's called a braced frame. Those are the two types, yeah? And that will heavily affect the effective length of buckling, okay? So let me show you this. This is the idealized charts. So brace members and sway members have different rules. So again, sway members, right, like you described, Caden, will do essentially like that when lateral, actually not even lateral, just when axial loads like compression and stuff push down on it, right? They're going to behave differently to how a frame which is braced like this, for example, would behave, right? Yep. So that's the first thing to consider. The second thing to consider is like you said, the end restraints or how it's connected essentially, right? So there's fixed connections, there's pin connections. Those are the ones we consider essentially. Oh, and free, I think. Oh no, that's still pinned. Okay. So these numbers, some of them are higher and some of them are lower, right? So essentially, the best way that I thought of explaining what K is the size of the C shape you can see on the diagram. Does that kind of make sense? So if that's the length here, L, our K is what percentage of it is the C shape? So for the first one, what percentage would you say is a C shape? 70%? Oh, it's 70. Right? So that's 70% of that is your C shape. Right? Okay, the next one. Pinned at the top and rigid at the bottom. 85% of that is C shaped. There's 100% of it is C shaped essentially, right? So here's where the L is equal to your effective length as well. Okay, what about the sway members? These ones are bigger. So how much of this is your C shape? The C shape goes off the page. Do you see how that happens? Yeah, so for sway frames, this one's like, bro, this one's C shape is like fucking like that. You know what I mean? And this one's C shape is also like that. That's kind of how they got these numbers. So what happens when you have a longer length? Is it more or less susceptible to buckling? So what happens when you multiply your length by 2.2?
And it becomes 2 by 2 times more.
Yeah, exactly. It's like as if your column or whatever is fucking massive because it's really, really susceptible to buckling if it's a sway. Yeah, if it's like in a sway member or whatever. Does that make sense? Yeah.
So, so that means sway members might be longer.
They're effectively longer. So you pretend that they're longer in your calculations than they actually are. And you exaggerate them to be worse than they actually are. Whereas braced members, they're braced so they don't move as much. And so parts of it are, like for example, fixed to fixed. Parts of it are like, it's as if only the middle portion of it is your length that you consider, which can buckle. Yeah. Yeah. Because that's like the part that's buckled. Does anyone want to have a crack at so actually, this is an anecdote. At work, the first thing I've really been learning, because I just started last week, is about columns and kind of like designing columns. And so I'm designing, do you guys know Scape? Maybe I fucking shouldn't talk about this. Okay, it's a building similar to Scape, Kingsford, right? Like on Anzac Parade, and so it's like a residential building, right? So it's concrete slabs and columns system. What kind of effective length do you guys reckon that they would consider for that type of building? Right. So let me just quickly draw it. It's kind of like this shape. You said 0.7, right?
Yeah.
So fixed and fixed on a braced member, kind of. Oh yeah. But firstly, do you reckon we would consider it as braced or sway for that kind of building?
Sway.
It would be sway based on the information I just told you, but they don't want it to be a sway building, right? In real life, because sway building is dangerous. You don't want to be in a building that fucking sways around, right? So what they do is they put a concrete core in. So that's usually like an elevator shaft that is like a really thick concrete walls, and so it doesn't shake around. That's their way of essentially making it braced, right? Okay, so say it's braced, based on the end conditions, right? Like the end restraints. What do you think that building's K factor might be in the ballpark of?
You're 185.
Yeah, that's perfect. That's basically what we use. Yeah. So not because it's exactly like this apparatus, it's because it's somewhere in between being rigid and pinned. Because it really is based on like how thick the columns are and crap like that. Anyway, whatever. Anyway, sorry, that was a bit of a tangent. But like, I hope that gets you thinking a little bit about how important the K factor is for buckling and everything. Just everything to do with column design. Yeah. Okay. There's one more thing I want to talk about, and that's gamma method. Like regarding effective length. So this isn't the only way to calculate effective length. So that's the table. They dedicate an entire week of your course, week 3, just on gamma method. Gamma method is kind of like what I said. It gets you considering the entire structure, right? And say you're designing a column within that structure. Gamma method is like, what is the rigidity of the beams that's connecting your columns at the top and bottom, and it's like a whole system approach for calculating K. It's just to calculate K, right? Yeah, does that make sense? Because in real life, we can't just justify it kind of based on like simplified diagrams and whatever. Yeah. Okay. Any questions? Right. That's gamma method basically. You'll see it. If you subscribe to my YouTube channel, you can see it in week 3's content, and you can see an example of it. Okay, radius of gyration. I talked about it a little bit earlier. There's a formula for it. It's just the number that you use to find like your modified slenderness ratio, essentially. That goes here. Yeah. Okay, any questions? That's pretty much all of compression. Okay, so flexure. Okay, and I kind of know what you're talking about with you said like the web was like susceptible potentially to buckling, I think. Oh no, and you were talking about the beam as if it was like being loaded like that or whatever, right? Yeah. So before we were talking about axial forces, right? Now, usually flexure isn't like 2 perfect moments or whatever on the sides. Usually flexure is a result of shear forces, right? There's like uniformly distributed loads and stuff like that, and that causes a moment, and it induces a bending moment, right, on your beam, right? And so the rules for buckling are a little bit different, okay? Let's go back to engineers' beam theory. So this is like, if you've done concrete, this is the most important topic in concrete. In steels, it's important, but it's somewhere in the middle of the course, and it's one of the harder topics, right? So, if I have my trusty bit of Play-Doh again, right, and I bend it like this, right? Basically, like we have an uneven distribution of strain along the depth of our section. right? So some of these fibers are being compressed, some are being pulled apart. Do you guys kind of know what I'm talking about when I say that? Yeah. Yes. Does everyone know what I'm saying when I say that? Because I remember the first time I heard that, I had no idea what that fucking meant. Okay, so firstly, strain. Do you know how I said that strain is kind of like displacement? So strain is fairly easy to understand when we're talking about like tension, for example. Strain is just how much is being pulled apart, for example, right? But it gets really complicated when strain varies along the depth of a section. So for example, what I've drawn here, right? Part of our beam is being pushed together and part of it is being pulled apart, right? So which parts are being pushed together, which parts are being pulled apart? Which is called, yeah. And the bottom is, yeah, in this specific case. So this is a simply supported beam or something. What happens if we have, what happens if we have a cantilever element like this, right? So it will deflect like this, right? Do you see how these elements are being pulled apart? Now the top is in tension. And the bottom's being compressed, right? Okay. But in this case, the top's being pushed together in compression and the bottom's being pulled apart in tension. This is like basic flexural theory, but you got to understand it, right, for this part of the course. Okay, here's where it gets funky, and here's where you kind of have to have a good understanding of the steel material curve. Do you guys remember how we were talking about the steel material curve and it looked like this? Elastic, and then flat, and then the strain hardening part? Yeah?
Yeah.
So let's quickly disregard the strain hardening part. Let's just talk about when it yields and stuff like that, right? That's what's happening in this diagram, essentially. So we're looking at different stages of stress here, okay? So essentially we're straining the beam by bending it more and more, right?
Yeah.
And what's happening with the material curve, essentially?
It's becoming more and more plastic.
Yeah, exactly, right? So, for example, what's happened in this very first one?
It hasn't yielded yet.
Yep, so on our material curve, we're like here or something, right?
Yeah.
Okay, what happens here at stage 2?
It's the yielding point, at like the yielding strain.
That's here?
Yielding strain.
Yeah, exactly. Right? That's what we call the first yield bending moment. Maybe not moment. The point of first yield bending. Right? What's happened here in this diagram? Yep. Has the entire thing plateaued?
No.
Which parts have plateaued?
Only the top and bottom part which have bent.
Exactly. So these regions have plasticized. Right? That's kind of what we're looking at. So we're straining the beam more and more like this. And do you remember how we said the top is in tension and the bottom's in, oh sorry, other way around. The top is in compression and bottom's in tension?
Yeah.
We were looking at the extreme fibers. When I say extreme fibers, I mean like the topmost and bottommost parts. But we have to kind of consider the entire beam, right? So those ones are the ones that yield first, the outermost parts. And then as you strain it more and more of it becomes yielded, right? Makes sense? Yeah. So what's happened in this last one here?
Becomes fully plastic.
Exactly. So that's called plastic bending. Yeah, that's it. Do you guys need a copy of this or not? Okay. So let's step back from that idea of the plastic bending and whatever for the moment, because we're gonna reshift our focus to another part, which is gonna depend on anyway. Section classification, right? So here I've just kind of drawn it. When we're talking about compact and slender sections, we're talking about the cross section, not necessarily like the length to width or whatever ratio of like the entire. So we're just talking about the section part at the moment, right? as you can see, if you make the elements thicker, it becomes compact, and so it's not susceptible to local buckling. So the local buckling and global buckling concept apply for both flexure, which is what we're looking at right now, and compression, which was the previous topic, right? It just applies throughout. Anyway, yeah, sorry. So back here, right? First yield bending is where the outermost fibers have what do you call it? Have yielded, just the outermost fibers. Okay. So what we're looking for is we want to calculate Z. Z is our elastic section modulus. Okay. And this is the way you're going to do it if you have a custom section. If you have a one steel product, you go to one steel, you find it on the table. It's easy. But for a custom section, it's harder. What you have to do is you kind of have to do this kind of like force analysis. Oh, sorry. You have to take the moments about the neutral axis. I'll explain it more in the yap that I'm going to do because I don't have much time. In week 4 or whatever. So stay tuned, subscribe. And then you divide out the strength, basically. Okay, whatever. You do a similar thing for the plastic section modulus, but you do it for this kind of arrangement, right? So you're doing it where the entire section has yielded, and you take the sum of the moments about the neutral axis. Okay, sorry, there's too much to explain on that right now, so I'll just move on. So for flexural design, it's very similar to compression design, right? You do the section check, and then you do the member check. The way you do it is a little different though, okay? So very similar to compression, we're gonna have either yielding, you're gonna have either yielding or buckling, section buckling happening on, I didn't paste this right, but yeah. Which is gonna govern our section capacity. And so we need our effective section modulus, right? Which you can find in one steel, or if it's a custom shape, lucky you, you're gonna need to do some pretty hard calcs, all right? So this is like assignment material. I'll just give you an idea of what's going on, but it's too much to cover right now. Essentially, you have to break down the section into the parts which won't buckle, similar to what we did for compression. Find like the ineffective, not the ineffective area. You have to look on a bunch of tables and find the classifications that are correct, plug in a bunch of numbers, compare numbers, determine the elastic modulus and the plastic modulus. That's like another step. All in order to find this effective section modulus, right? Because what we basically did is, okay, so just consider like an I-beam. Before, this was the first yield moment is where like just the tips have yielded, right? That's one extreme. The other extreme is where the entire section has yielded. And at some point in between is where we consider our section to have failed in yielding, right? It's not when just the outermost fibers are yielded, and it's not when the entire thing is yielded. It's somewhere in between. That's what these calcs are about, and it's a function of how slender your elements are. That's what effective section modulus is talking about, right? Make sense? Yeah? Okay. That's the aim. There's a bunch of formulas. I won't have time to cover them. There's a lot of reading of the standards in this part. But yeah, that's how you do the section failure checks. The member failure checks, the member failure checks are a little bit harder because it requires you to understand a lot more context on steel connections. So there's a lot of, there's something called restraints. It's just how you kind of prevent your member from buckling. So I'll give you an example. If you have a, if you have your like I-beam, and then at certain points you have, so you have a fin plate or whatever, and then you know, it's attached to another member essentially. That counts as a type of restraint, and there's a lot of details in the code about how things are restrained. And basically restraints kind of act as like little nodes for where buckling can't happen, right? So like instead of before, buckling could have happened along the entire beam. Now that kind of fixes that member in place, right, if it's fully restrained, and buckling can only happen within that span. Does that kind of make sense? So restraints are kind of like intermediate parts, which are like not really supports. You don't consider them as structural supports, but parts which reduce like the buckling length, right? Yeah, there's a bunch of theory on it. We'll cover it later. Yeah, that's pretty much. And then there's a moment modification factor. So the fastest way to explain this. You're taking the bending moment diagram of a beam, and how do I explain this? And based on how like the bending moment is distributed, whether it's like evenly distributed or there's certain parts which have like high bending and low bending, will also affect how susceptible your member is to Euler buckling. I don't know. That's the best I got.
Is it just like factoring the actual bending moment diagram?
Oh, so, yeah. So sorry, I should. You have your bending moment diagram after you've factored the loads. That's where the star comes from. So you do all your G and Q factoring, and that bending moment diagram at certain intervals, right? The quarter points and the midpoint. That's what's gonna be plugged into your formula. It's just basically about how even your distribution is. Yeah. And the max is the M part. Yeah. Slenderness reduction factor is kind of similar to how we had our gamma. Sorry, is it gamma? No, that's lambda. Yeah, lambda n from compression. So it's to do a slenderness ratio. Except like our effective length, instead of just being a single k factor L, right? There's a bunch of things that will affect it, including what I talked about with like the restraints and stuff. There's like load types and like a bunch of random things, right? But yeah, that's what I'm saying. Like flexure is one of the hardest topics essentially, because there's so many things to consider. Load height, like bro, like who even thinks of this shit? Load height, like where the load is applied on your beam, things like that. So yeah, and then another thing is like reference buckling moment. So there's a lot of imperfections with shit. How do I explain this? Okay, we'll get around to it. There's too much. Okay, that's the end of my crash course. But I'll quickly show you what my mate showed me on compression. Oh shit. On connections, I should say. I'll chuck these in the folder as well, but they're unverified. Not that I don't trust him, but I'm just saying they're unverified. Okay. Essentially, there's going to be two types of connections you consider in this course. So connections, again, it's just how two members are connected together. There's going to be bolts and welds. Has everyone heard of those? Yeah. So bolts, as you can imagine, are like the easier of the two to install. And you consider them as like single points, essentially, on like diagrams and stuff, right? Just the centroid of where the bolt is. The other one is welds. Oh, what the hell? Group bolts, weld, okay. Welds, have you guys seen welds, like in real life or whatever? Yeah, I'll just pull up a picture. the fuck? Oh yeah. So welds look like this, right? They like get a torch and like a rod of metal, and then they melt it along. So essentially, you consider it in this course as like a straight line. Yeah, and in terms of like, you're gonna find like the centroid of a bunch of welds. You consider them as like straight lines. Welding, I guess in real life, is more expensive because you have to like hire a welder to come onto site, and they can fuck it up because it's like a higher skill thing. So generally you design with bolts wherever possible, and you avoid welding like the plague. But in this course, there's going to be both, basically. Yeah. So I think they'll do bolts first and then welds.
Isn't welding stronger?
Yeah, so welding, like, it's not like they don't weld. So welding, if it's done in a factory and it can be prefabricated, that's actually good, because then they just need the welder to do a bunch of different jobs like in the factory. Or sometimes if it's like a mass-produced thing, then they have a machine weld it. And it's like very precise, right? But like on site, it's like the Wild West. So like welding it's very hard as well. Like, because if you're out on site and you're welding something that's like 6 meters long, there's a good chance you're gonna fuck it up, basically, right? Welding is very strong though. Anyway, but for most assemblies, they'll try to bolt the elements together on site. Yeah, because that just needs a power tool or something. Yeah. Okay. Any questions?
You know the part where you skipped, you said it's like 4 pages of steps for one of the topics.
Let me find it. One sec. Sliding. So that one, right? This one? Yeah. I will in 4 weeks. So I'll record them as I go. I'm still making the notes. Yeah. I'll make weeklies. Yeah. So stay tuned, stay subscribed. So custom shapes. This is basically only assignment material. You're not going to expect it in your finals because this takes so fucking long. This is like, you get a take home for a Flexural assignment. They give you a custom shape, and you're like, fuck, this is going to be like my life for the next like week.
Custom shape. Is it individual for everyone?
Yes. So it'll be like, yeah. It'll be like, yeah. It's like basically a ZID and everything. So it's like this length or whatever. I mean, this width, for example, is like 3 times your ZID's like 5th digit or something like that. You know, or I don't know. That's probably bad. It's probably like 300 times. I don't know. Anyway, whatever. 100 times your ZID's 5th digit or something. It'll be some stupid shit like that. Okay, any other questions? You're welcome to leave if you got no questions. Otherwise, I'll be here. Yeah. Oh, you got an announcement?
Oh yeah, guys. I know it's pretty late, but I do.